Okay, and 2D manipulators example would be a double pendulum. And if you recollect, we had developed this methodology to compute the positions. It was using this homogeneous matrix. The homogeneous matrix HI with respect to frame I minus 1 was given by R I with respect to frame I minus 1. The origin of frame I with respect to frame I minus 1, 0 will be 0, 0, 0, and 1. So x0, y0, x1, y1, and so on. So this is the origin I with respect to I minus 1. And then the rotation is associated with this. Okay, so we can then extend this idea to, let me just put the dimensions to. This would be a 4 cross 4 matrix where this would be 3 cross 3, 3 cross 1, 1 cross 1, 1 cross 3. So it makes it 4 cross 4. Okay, now we can extend the same idea to generic three-dimension motion, because now we're looking at 3 dimensions. We can write so this is in 2D. In 3D, we'll have exactly the same expression except that this would be, no, my bad. Somebody should have corrected me. This is not right. In 2D, we never wrote, not 4 cross 4. This was 2 cross 2, right? This was 2 cross 1. This was just 2 zeros. It was 1 cross 2, 1 cross 1, and it was 3 cross 3. So here is what I switched it by mistake. So this should be 3 cross 3, 1 cross 3, 3 cross 1, 1 cross 1, so 4 cross 4. The only change being that now we write rotations as a 3 by 3 matrix. So remember, I wrote rotations for the XYZ Euler angles. That's pretty much what it will come there. The origin of the frame is no longer XY, it has XYZ, so it's 3 cross 1. And then this last line or the last row is just a placeholder to make the calculations easy. Now we can use this in what is known as a convention for figuring out rotations, the kinematics for a manipulator. Okay, so before we use this, there are essentially 2 types of, so we'll use this. Okay, so just hold on to that. Let's talk a little bit about the manipulators we'll look at. We've seen manipulators like this in the course. And then there are other types of manipulators which look like this. Okay, the difference being that this is open and this is a closed chain. So there's at least one loop joint. The kinematics of closed chains are much harder than open loop joints, and we'll only look at the open loop manipulators, not in this course. Okay, so we'll only look at open link manipulators. So let's develop some terminology for 3D manipulators, and then we'll use the 3D manipulators with this homogeneous matrix to write the kinematics. Okay, I'm going to show it as a planar manipulator, but there's no reason why it is planar. It could be that the axes are not along the z, but along the x or y. So let me just cross open link chain. Okay, so this dots indicates there are some links between those two dots or three dots. Okay, we'll call these joints joint I, so joint 1 in this case, joint 2, joint 3. Let this be joint I, and then as you proceed here, somewhere is joint J, and then this is our, yeah, sure, just continue. This is my last link. This joint. So then I have links. This is link 1, link 2, link I, link J, and link N. Okay? And when I'm talking about manipulators, I want the manipulators to do something useful. So for example, the last link might have a gripper, and the gripper needs to grip on something. So we are always interested in the location of the last joint. Say this is where the end effector is. And that end effector is going to grip something. So our whole goal in this manipulator business is to figure out, either given the joint angles, what is the position of the end effector, or if you want the end effector to be at a particular position, what are the joint angles we need to set so that that end effector is in the location we care about. Okay, now comes frames, which is what we'll be using throughout. Let's assume there is a world frame, X, Y, Z. And then we can attach a frame to each link. This is 1, this is frame 2. This is going to be frame XI, YI, ZI. This one will have frame XJ, YJ, sorry, XJ, YJ, ZJ, and so on. So this is the ground. Okay, now it's the time when we'll be using the H's, which we had. The H's are something which tells the position and location of the frame, right? So J is the link which is distal. Distal means further away. And you can find its location with respect to the link I, which is proximal or closer towards the ground, by composing these H matrices, HI plus 1, H I plus 1, I plus 2, so on till H J J minus 2. This is if I is less than J. Okay. Remember that you are numbering from 0 all the way to N. In this case, as I've shown it, I is less than J. And so you will just take this H matrix which I wrote down and you multiply them. If you want to do, if you want to find what happens when I equals J, that is joint I is the same as joint J, that is simply I. And then if you want to figure out what happens if I is less than, greater than J, that is, in other words, if you want to describe the position of, so this is describing the position of joint J in frame I. In other words, it's telling you how this link will move as a function of, or as observed from an observer here. Okay, that's what this is telling you. If you want the opposite way, you just have to invert the matrix. So you just say H I J inverse. This is the homogeneous matrix, which I wrote down earlier. It's a 4x4 matrix. And this is an identity. In 2D, we had this homogeneous matrix, which is a 3x3 matrix composed of R's and O's, where R is the rotation and then O is the origin. Right, and then we had used this to pretty much talk about 2D manipulators, double pendulum, and so on. In 3D, what we'll do is we'll extend this to a 2x3 R matrix and a 3x1 O matrix, where O is the origin of the frame. And this matrix homogeneous transformation is going to be 4x4. So what is R? R is something which comes from the three-dimensional rotations. I talked about the Euler angles, and R was in those Euler angles of 3x3 matrix. So for a three-dimensional motion, you will have, you can have pure rotation, you can have pure translation, and then if you want to compose something of rotation translation, you just start multiplying these homogeneous matrices together. So let me just define these homogeneous matrices first, and then we'll use that to get to Denavit-Hartenberg convention, which was the handout I just gave today. So what is the homogeneous matrix associated with rotation about the x-axis? Now, x-axis, we used Euler angle phi. And so what you'll do is we will write the homogeneous matrix by taking the rotation matrix first, corresponding to phi. 0 cosine phi minus sine phi, 0 sine phi. And then I'm going to assume that the origin is 0, 0, 0, but if it is different, you just put it there. So this is the rotation matrix. And this is the O matrix, which is the origin of frame attached to this particular angle phi. And then we need to put these zeros in order to make it complete. Okay, the zeros and zeros and ones makes it a 4x4 matrix. And then when we multiply things, you will see that we can actually do useful things if we have it as a square matrix. This is hx phi. We have hy theta. That would be cosine theta 0, sine theta 0, 1, 0, minus sine theta 0, cosine theta. Again, 4x4. We can keep going with rotation about z-axis, span angle psi, cos psi, minus sine psi. Okay, so you just like you have a system which has revolute joints, we've so far never looked at systems with prismatic joints. So prismatic joints are involve linear motion. You could also have a joint which has linear motion, in which case you would write a similar expression. Let's say that the translation for the prismatic joint is ax about the x-axis. So the joint is along the x-axis. I think the closest thing you did was the cart pendulum, where you had a prismatic joint which is showing the motion of the cart, right? Also the rimless wheel, you had an X and a Z. That would be a prismatic joint. So here, what we do is there is no rotation. So we'll have the identity matrix. And then corresponding to the motion of the frame, we'll have AX 0, 0, 1. And similarly, we can write hy ay, which will be 1, 0, 0, 0, 1, 0, 0, 0, 0. And then 0, ay, 0, 1, corresponding to motion along the y-axis. And then we can write hz2. This is all prismatic. This is revolute. Okay, with that, we are ready to tackle Denavit-Hartenberg convention. Okay, so this is a convention which is used to represent kinematics of a 3D manipulator, also a 2D. It has 4 numbers associated with it, and corresponding to those 4 numbers, there are four homogeneous matrices. Let me first define those homogeneous matrices and then come to the theory. And that's also in the equations, also in the handout. So easier. Have it here. Let me just write it here. So Denavit-Hartenberg convention. Called DH. It's a method to represent kinematics of a manipulator So what's so special about it is that, I should just put it here maybe. It's an efficient method to represent kinematics or manipulator. Okay, why it's efficient? We'll come to that in just a bit. Let me just write the homogeneous matrix associated with the Denavit-Hartenberg convention. Okay, it is composed of 4 homogeneous matrices. HZDI, HX AI, and HX alpha I. Okay, so what would HZ theta I be? Well, we've already seen what rotation about the z-axis would be. It would have a rotation matrix associated with theta I. So I'm going to write a shorthand notation because I need a lot of room to write this. Where C theta is cosine theta I, S theta is sine theta I. HZDI means that it's translation about the z-axis, and the translation is di. So first write the zeros for the rotation matrix, sorry, identity for the rotation matrix, and then we just put 0, 0, di. Okay, then we have translation about the x-axis, and that's ai. So again, identity on the rotation matrix, and then ai 0, 0, 1. And finally, there is rotation about the x-axis, 0 c alpha I minus. To get some room here. 0, 0, 0. Okay, here, C alpha I is cosine alpha I, S alpha is sine alpha I. Okay, so these parameters, theta I, pi, ai, alpha I are known as the DH or Denavit-Hartenberg parameters. Okay, DH parameters. Okay, so what it's doing is it's basically laying down the orientation and the position of a link, right? Because what homogeneous matrix does is basically gives us the origin of the position and orientation of a frame, but the frame is attached to a link, and so it's giving us the position orientation of a link. Now, the thing about three-dimensional kinematics is that anything in space needs 6 numbers to describe it. There is positions, which is 3 numbers, x, y, z, and there's orientation. If you use Euler angles, it will be theta, phi, psi. So it requires 6 numbers to specify anything in space. But DH convention is telling you that you don't really require 6 numbers, you only require 4 numbers. So that looks like there is some information which is being removed, right? How can you represent something which requires 6 numbers with just 4 numbers? The thing is that the convention uses an efficient way of describing the axis. And by describing the axis in the way I'm going to tell you, you can actually get rid of 2 numbers. So that is why it is called efficient. That is, even though you require 6 numbers to describe a link, you're only able to do it with 4 by defining these axes in a special way. Let me write that down. All those 6 numbers, that will be x, y, z, theta, psi, phi, are needed to describe a link, position, / orientation. TH does this with only 4. Okay, it's possible because DH uses a special way to define the axis of the links. So that's the key, the special way to define the axis of the links. Okay, and the special way is that the special way is the 2 things which it does. One is axis of xi is perpendicular to vi minus 1. So what that means is that the axis of link I, the x-axis of link I, is right angles to the z-axis of the previous link. Okay, that's why it's I minus 1. And the second fact is that axis of xi is intersecting with vi minus 1. So these 2 constraints eliminate 2 parameters, and that's why we can get rid of 2 numbers out of 6. Get rid of 2 parameters. Okay, now there is a proof for this, and I don't want to get into the proof. We'll just be smart users of the system. The reason why I want you to learn about DH is because if you look at the specification of manipulators, you will see that they'll give you a DH table, which will have these parameters. So if you know them, you can then go on, describe the kinematics, and then use that to do something useful. Okay, so the handout has, it basically has the HII-1, page 1. It also has some other information, but the main thing we'll be using here is this algorithm, which I've written down there. Okay, so the algorithm is basically what it does. It basically takes the manipulator. You need to know what the axes of the degrees of freedom are. Once you know those axes, you can then use these steps in order to fix the coordinate frame, right? I said the coordinate frame is very important because unless you have the coordinate frame, you cannot find the DH parameters. That's step 1. Step 2 is we'll generate the DH parameters just by looking at that figure with the axis. Finally, we'll apply this transformation. This is now H. When you take all these 4 matrices and multiply them together, you end up with something like this. So I written that down. And then in order to compute, so let's say that we have multiple links, right? So this is world frame. 1, 2, 3, 4. Your n is equal to 4. What we're typically interested in is we want to find the end effector position. So what you'll do here is you will write H40 as H10, H21, H32, H43. And when you do this multiplication, what you'll end up with is something like this. When you end up with this, what you simply do is, this is the orientation of end effector. And then this is the position of end effector. Okay, so which is that? And why would you want that? Well, most of the kinematic problems with manipulators are pick and place. So you want to know where your manipulator is so you can pick something, and you need to go somewhere else and place it. That's like the most important thing. So that's why you want to know what the end effector position is. And of course, the orientation, because if you don't know the orientation, you cannot graph something, right? And so that once you have these H matrices, it's just a matter of putting them together. How do you get the H matrix? For each line, you'll have one H matrix. So you just have to then multiply them together. Okay, so steps 1 and 2 are kind of the harder ones, and then 3, 4 is, step 3 is pretty much something you can easily do using Python or any programming language. Okay, so let's get into this algorithm, and I'll show you examples, and then for your homework, you basically solve problems based on this. I have also put this figure, which is kind of helpful. When you're going to, after you assign the frames, this thing will help you to assign, to figure out what the where is D? Here's D. And then alpha I. See, this is AI minus 1. Okay, this is theta I, and this is I think alpha I. Okay, so you can use this, but I have an easier way of doing it. It's up to you. This is from the book Spong, the book by Spong, but I'll show you an easier way of getting this without having to remember this figure or know this figure. So let's solve problems. That's probably the best way to learn about it.